Let's see. Let's see the decomposition of H2O2. Okay. How is this applicable and how it is used as a first order kinetics? Normally, the decomposition happens as a first order kinetics. So if I say that at time t equal to 0, some A moles were present and there was no water or oxygen. After some time t, let's say some X moles have been lost from peroxide to form X here and X by 2 moles here. Got it? Then I would say the amount that has formed here will be directly proportional to the volume occupied after time t. And this V represents basically volume of O2 at STP. Right? That how much amount of volume is O2 is being occupied at STP. Now let it put it for a long time till the entire decomposition is done. So there will not be any peroxide left. So everything will dissociate into A and A by 2 moles. Now this A by 2 moles is proportional to another term we can write, which we call it as V infinity, which is the volume of O2 at STP after a very, very long time. Now, if I put this with respect to time, that is 2.303 by K log of A by A minus X. This is the first order kinetics equation. And you know that if A by 2 is proportional to V infinity, which implies A is directly proportional to 2V infinity. Likewise, if X by 2 is proportional to Vt, X is proportional to 2Vt, which means if I take this as A by 2 minus X by 2, that will be proportional to V infinity, or let me put this as A and X directly. So A minus X will be proportional to 2V infinity minus 2Vt. And since A and A minus X is seen how it is proportional to the volume, I can say A by A minus X will be equal to 2V infinity by 2V infinity minus 2Vt, which is equal to V infinity by V infinity minus Vt. So if I substitute that back, I would get this as 2.303 by K log of V infinity by V infinity minus Vt. So this will be the first order kinetics equation, first order kinetics equation with respect to volume terms. Correct? So if the volume terms of oxygen at STP is given, right, we can use this. Now, if you recall, this volume basically is also called as the volume strength. And you know that volume strength of peroxide, which means how much amount of oxygen is released, is proportional, is equal to molarity into 11 by 2. So if you check out the molarity at this point and molarity at this point, it might be different because at this infinite time, you'll hardly have any A. So that means we cannot have any molarity as such. Got it? So we have to check what is the initial molarity and what is the molarity after time t. So we can say this will be, let's say, if you have Vs, right? Uh, you know that A is proportional to 2Vt, so which is proportional to 2 times of m into 11.2. So let us put this as m naught initially, and A minus X is proportional to 2Vt, which is proportional to 2m1 into 11.2. Okay, so here we can write it as, okay, we could write this as m naught minus m1, m naught by m1. So we can write this as A by A minus X is proportional to m naught by m1. Got it? So instead of this, we can also replace that with molarity term here. That is how much amount of molarity it has. Okay. Sorry, sir. Below it will be m naught minus m1. All right. So same thing. If the molarity of the peroxide is given, we can use that logic, write this as m naught by m naught minus m1, because the rest of the factors are constants that will get cancelled. Hmm, okay. Right. Clear with this? Everybody, please check it out. How this can be used as another application here. See, if you are making titration of peroxide with KMnO4, you know that by equation it is like this, right? 2 times of KMnO4 plus 5 times of peroxide in an acidic medium will give you 2 times of Mn plus 2 plus 5 moles of O2 plus 5 moles of H2O, right? This will be the equation for oxidation of peroxide. Now, number of equivalents any point of time should be equal to KMnO4's equivalence. So no, number of moles into valency factor should be equal to N1 into V of KMnO4. And now suppose number of moles of peroxide, which is proportional to how much volume of KMnO4 is used, because N is constant, then I can say if you have A proportional to V naught, which is the initial volume required by KMnO4, A minus X will be proportional to Vt, which is the volume of KMnO4 required at time t. So A by A minus X can be replaced by V naught by Vt. So these two terms can be directly utilized. If the question is only about in terms of volume of KMnO4, then we can directly use this and get it. Got it? So I hope this part is clear, everyone. One second. Is about pseudo first order kinetics. When do we first see? Imagine I have two components reacting to give product. Everyone, I'm audible? I'm here.
Yes, sir.
Right. The T equal, I have 10 moles here.
Address, sir.
Up. One second.
Let me check. Suppose if you have 10 moles and imagine on the other side B has something like 10,000 moles. So obviously after some time t, we expect maybe some 2 moles have lost from here. So another 2 moles will be lost from here, correct? If it is an elementary reaction, as per rate law, rate can be written as K into concentration of A power 1 into B power 1. And you notice that this will be K into 10 minus 2 raised to power of 1 and 10,000 minus 2 raised to power of 1. Now I can say this 10,000 value is almost the same as that of 10,000 minus 2. Even if you subtract minus 10 also, hardly that is going to change. Hence, we can assume that the concentration of, okay, we can assume that the concentration of B here is almost constant. So if I put this as a constant, I can write rate is equal to some K into K constant, that into concentration of A power 1. So that implies the order of the reaction will be equal to 1. So when one of the component becomes, highly concentrated or extremely high number of moles present in it, then that will lead to the formation, of uh, first order kinetics. Correct? So this is what we call it as pseudo first order kinetics. Pseudo first order kinetics. Clear? Now, pseudo first order kinetics is observed. Pseudo first order kinetics is observed whenever something like water is used. Water is naturally a high concentrated solution. Why? The density of water is 1 gram per ml, which is 1000 gram per liter, which means if you notice the concentration of water, it is 1000 by 18 into 1 liter, which makes it 55.5 molar. So you can see the concentration of water naturally is very high. And when you are adding something like glucose, sucrose, these are all at a very low concentration, maybe zero point 0.1, zero point 0.2, maximum 1 molar concentration. Correct? Such concentrations, if compared to that of water, that's quite less. That's why we can assume that there is hardly any change in the concentration of water. So this is an example which I'm taking right now. You can see hydrolysis of sugar or sucrose, which is also a pseudo first order reaction. This is also called as inversion of sugar. The process is called inversion of sugar. You can notice that sucrose, when you add it to water, it will give glucose and fructose. While if cane sugar or sucrose has a number of moles initially or a concentration initially, and water concentration is very high, there was no glucose and fructose to start with. So since there is only glucose and water has no optical activity as such, so it is only, sorry, sucrose. Only initially we have sucrose. So that sucrose is showing an optical rotation of, let's say, R naught. And after some time t, some X amount of sucrose is lost to give X moles of glucose and X moles of fructose. And the rotation at this point on the polarimeter is RT. And at infinity, when there is no sucrose, then you get all of this A converted into A moles of glucose and A moles of fructose. In that case, the optical rotation is found to be R infinity. Correct? These three datas would be given to us. That sucrose is a pseudo first order kinetics, sucrose hydrolysis is a pseudo first order kinetics, and their optical activity or optical rotation initially, after time t, and after infinite time, these are the ones. Naturally, sucrose is a dextrorotation, glucose is a dextrorotatory, and fructose is a levorotatory. Okay, this is levorotatory. Now, what you need to realize is that when you write the rate law, so you will write rate R is equal to some constant K into sucrose concentration power 1 and H2O concentration power 1, which I can write it as K dash into sucrose concentration power 1, which makes it pseudo first order kinetics. Pseudo first order kinetics. Okay. Now you know that at t equal to infinity, you know that 2a is proportional to R infinity. Okay. So that means what is that 2a here? That 2A is because of glucose and fructose together. And you know that glucose and fructose is forming in equal amounts. It doesn't happen that glucose quantity is more and fructose is less or something. They always form in equal quantities. Therefore, I can say 2A, which is glucose concentration plus fructose concentration together is showing an optical rotation of R infinity, right? So this is the optical infinity. Then for 1 mole of glucose plus fructose combination, how much rotation we should get? R infinity by 2A, correct? Now, if it is for 2x moles of glucose plus fructose together, then how much optical rotation it should show? R infinity by 2A into 2x. Similarly, on the other side, if you notice, for only sucrose, for sucrose, I can say A is proportional to R naught, isn't it? Because initially, when there is A, it is only proportional to R naught. Because if the concentration of sucrose is more, then the optical rotation will be more. And now, if I take it for 1 mole of sucrose, it is proportional to R naught by A. After time t, how much sucrose is left? A minus X. So for A minus X moles of sucrose, the optical rotation will be R naught by A into A minus X. Correct? This is how much we found. Now, let me go back to this. At time t, at time t, correct? The rotation RT is because of both sucrose as well as glucose and fructose mixture. So at time t, I can say rotation is because of sucrose and rotation due to glucose and fructose together. And at time t, how much amount of sucrose was there? A minus X. For A minus X, how much should be the rotation? It should be R naught by A into A minus X. And glucose and fructose at time t was giving R infinity by 2A into 2x. The 2 will get cancelled and this will be RT here. So I can write this RT, correct? So what I'm doing to make it more simplified way, I am subtracting R infinity on both sides. So I'll get R naught into A minus X by A plus R infinity into R infinity into X by A minus R infinity. So now I'll get this as R naught into A minus X by A plus R infinity will come common and I'll get X minus A by A. Correct? This is what I'll get. Now you can see these two things can come common here. So in that case, I will write this as, A minus X by A coming out to be common into R naught minus R infinity. So now if I bring this entire term A by A minus X to the left hand side, I will get A by A minus X is equal to R naught minus R infinity by RT minus R infinity. Now, as per first order kinetics, we know that T can be written as 2.303 by K log of A by A minus X. So T will be equal to 2.303 by K log of, what did we get? R naught minus R infinity by RT minus R infinity. This is what I will get. So instead of expressing that in terms of A by A minus X, now you can express the rate law in terms of optical rotation, given at different times. Everyone, I hope all of you understood this, how I derived it. So just please go through it once quickly, then we can go further. Next one is about ester hydrolysis. Ester hydrolysis is also a first order kinetics. An ester, adding it in water, you will get acetic acid and ethanol. Now, this is also a single step reaction. Its molecularity is 2. It is a pseudo first order kinetics. Rate can be written as K into ester concentration. K is a rate constant. Rate constant is always proportional to concentration of the catalyst. Now, this is very important. Usually, when you add the catalyst to the reaction, what is the effect it will produce? Let's see that. Okay, adding catalyst. Whenever you add a catalyst to the reaction, first thing it will increase the rate of reaction. Rate of reaction. Increase the rate of reaction means R is equal to some constant into concentration of the reactants, correct? But does it change the reaction concentration? No. So what is that exactly increasing is the rate constant. So basically increasing concentration of catalyst, if it increases, the rate constant of the reaction increases. Got it? That's one thing we should understand. Second thing, rate constant, rate increases equally in both forward and backward direction, forward and backward direction in equilibrium reactions. In equilibrium reactions. So rate increases the rate constant in the forward direction as well as rate constant in the backward direction, but in equal magnitude. Okay. Therefore, K of equilibrium does not change. Okay. If K equilibrium does not change, correct, then all the state parameters, all state parameters like free energy, enthalpy, entropy, internal energy does not change on adding catalyst. This is something which you will keep on listening to these points again and again with various topics. You will listen the same things in equilibrium, here, surface chemistry, got it? Wherever the catalytic part will come, you'll always listen to these terms. So the first point is important for us, that the rate constant is actually proportional to the concentration of the catalyst. And you see ester hydrolysis, more often or more frequently we see happening in acidic medium. So in acidic medium, if you increase the concentration of an acid, naturally it will increase the rate of the reaction. So you can see if you are comparing a 1 molar HCl as a catalyst and 1 molar H2SO4 as a catalyst, so definitely the H plus concentration in H2SO4 is more. Therefore, the rate constant of H2SO4 reaction would be more than rate constant of HCl. Hence, the rate using HCl will be less than rate using H2SO4. If K value of this one is greater, then the T half will be lesser. So half-life of H2SO4 will be lesser than half-life of half-life of HCl. Got it? So I suppose all of you got this point. Please check this out quickly. Then we'll go ahead. If there is any point which you didn't understand, please get back to me. In case of an equilibrium reaction, I told you that uh, catalyst will increase the rate equally in the forward direction as well as the backward direction. So now let's go through this case. Kinetics, how does it vary if you have the first order? On both directions, A to B is also a first order, B to A is also a first order. Now, before going into further details of it, we need to learn some basic terms here. That is If you are going in the forward direction or a backward direction, what are the simple things you need to understand? A going to B, if KF, this is the this is an elementary reaction. Similarly, B going towards A with KB is also an elementary reaction. Is also an elementary reaction. Correct? So since it is elementary reaction, rate in the forward direction, RF can be written as KF into concentration of A, and rate in the backward direction can be written as KF into backward direction. Sorry, KB into backward direction. Right? So this much we should understand. Now let me write down this part, that A to B, if you compare KF to KB, what I can say, at time t equal to 0, A, and at t equal to t, this will be A minus X and X. And at equilibrium time, this will become A minus X equilibrium and X equilibrium. Got it? And see, I can write this as rate of disappearance. Okay, rate of disappearance of A can be written as rate in the forward direction as Kf into A, and disappearance of B can be written as K backward, which is Kb into B. Okay. Now you know that at equilibrium, rate of forward direction is equal to rate of backward direction. So which implies K forward into concentration of A is equal to K backward into concentration of B. So you know that K forward into concentration of A is A minus X EQ, and KB into this is X EQ. Done. This is what we have. So from here I can write KB by KF will be equal to, okay, KB by KF will be equal to A minus X equilibrium by X equilibrium. Now this we will be using a lot of times, so please do remember it this way. KB by KF is equal to A minus X equilibrium by X equilibrium. If you write the rate law in terms of B, okay, rate of rate with respect to B, if at all I write, this is dB by dt, correct? dB by dt, and you see that dB by dt, correct, will be equal to d of x by dt, because at time t the concentration is x, and that will be equal to k forward into A, because there is an uh, gain of rate in forward direction, and there is there is loss of rate in the backward direction. This is the net rate of B, net rate of formation of B. Hence, I can write dx by dt is equal to kf into A minus x minus kb into x. Now you see everything is in terms of x. So kf into A minus x minus kb. Now can I write this kb as kf times of this entire thing? So that's what I'm trying to use it here. So that is kf into A minus x equilibrium by x equilibrium, that multiplied by x b is concentration x, correct? So now we have dx by dt is equal to kf into, if I take kf common here, so what do I get? I'll get A into x equilibrium minus x into x equilibrium minus of ax plus x equilibrium into x, this whole divided by x equilibrium. This is what I have. So from here I can write kf into, you can see this x equilibrium term will get cancelled, so I will have this as ax equilibrium minus ax divided by x equilibrium. Got it? So I suppose this part is clear. So I can take this a common. So kf into a, that is x equilibrium minus x by x equilibrium. Got it? Now if I take this to the other side, what do I get? Dx by x equilibrium minus x, that is equal to kf into a by x equilibrium into dt. Now we have appropriate uh, variables on both sides. So you'll have dx by x equilibrium minus x, and dx varies from 0 to x, that is equal to kf into a by x equilibrium, because these are all constant, 0 to t dt. Now if I integrate this, I will get this as minus ln x equilibrium minus x, and that is going from 0 to x. That is equal to kf into a by x equilibrium into t. So if I substitute that, I will get this as ln. First, I'll substitute 0 and x because of this minus. Okay. So ln 0, if at all I put, that will be x equilibrium by x equilibrium minus x. So that is equal to kf into a by x equilibrium into t. Correct. Now, earlier we have learned that k backward is equal to k forward into a minus x equilibrium by x equilibrium. This was our equation 1. So now if I open this, what it appears like is that k forward into a by x equilibrium minus k forward into x equilibrium by sorry, that's it. That will get cancelled, this one. So from here I can write that k forward plus k backward actually can be written as kf of a by x equilibrium. So now this part I can actually replace with this one. So therefore, we get this final equation. So ln x equilibrium by x equilibrium minus x is equal to k forward plus k backward into t. So these two terms must be given to us to solve it. So this is how you can generate the first order kinetics for an equilibrium reaction. Clear, everybody? So quickly go through it once. Check out how we have derived it from here. Check. If A is giving products, some reactant A is giving products, and let's say if this is a second order kinetics, then at t equal to 0, let's say initial amount is A naught, okay, and at time t equal to t, this will become A minus x or AT. This may be x or any amount, we doesn't matter with that. So rate R will be equal to rate constant into AT power 2, which implies minus dA by dt is equal to k into a square. So which also implies dA by a square is equal to minus k into dt. So I can integrate that dA by dt from a naught to at, sorry, dA by a square is equal to minus k into 0 to t in dt. As I integrate, I will get this as minus 1 by a, correct? So a raised to power of uh, minus 2 plus 1 by minus 1 from a naught to at is equal to minus kt. That minus will get cancelled. So what do we have here is 1 by at minus 1 by a naught is equal to kt. So this is the expression or integrated rate law expression. Integrated rate law expression for second order kinetics. Okay. This seems more like y is equal to, you know, mx plus c, where y in this case is 1 by t, and x in this case is t, and y-intercept is 1 by a naught, and slope is k. Got it? Since rate minus dA by dt is rate, so rate is equal to k into a square. Correct. With respect to concentration A, it will always increase. Correct. So with respect to concentration A, as the A concentration increases, rate will exponential, parabolically increases here. So, and minus dA by dt with respect to time. With respect to time, what would happen? The rate basically A here will be equal to some constant term we can get. That is, if I write that same term here, I'll get like this. Got it? 1 by A naught plus KT is equal to 1 by AT. So therefore, AT is equal to 1 by A naught is some constant plus K into T. So it is like, you know, inversely proportional. So therefore, if I compare this term here and I need to square it, for example, if I take dA by dt with minus sign here, which is the rate, so that rate will be equal to k into at square, so which is 1 by k dash plus kt whole square. So you can see basically this rate versus t is inversely proportional. So if the t increases here, the rate drastically decreases. So it will almost go like this. Correct? So these are the three graphs you should know for second order kinetics. Half-life. So if you notice the half-life, T50, I mean, from here T50 is when AT becomes A naught by 2. Then if I substitute that value here, so I'll get this as 1 by A naught by 2 minus 1 by A naught is equal to K T50. That implies T50 is equal to 1 by K into A naught. Correct? So this will be the half-life for second order kinetics. Clear, everybody? Everyone look into it. Please check if there is any problem, let me know. If you notice the T half, basically the T50 is inversely proportional to A naught. So it will be a rectangular hyperbola like this. And if I write in terms of 1 by A naught, it will be, going as a straight line this way. Okay. So these are the two other graphs which you need to know. Next, let's see if we are deriving this for an nth order kinetics. So in case if you have nth order, a raised to power of n, in that case, how do we derive this? Check it out. At t equal to 0, right? I can write this as a naught, and at t equal to t, this is at, which is a naught minus xm. Correct? So now minus dA by dt is equal to k into a raised to power of n for nth order kinetics, which implies minus dA by a raised to power of n is equal to k into dt. So integral dA by a raised to power of n a naught to at must be equal to k into t. Sorry, k into integral of 0 to t dt. Okay. So now I can write this as a raised to power of minus n plus 1 by 1 minus n is equal to minus kt. Okay. So that minus will go on the other side. So which implies I can write it as a raised to power of 1 minus n by n minus 1 is equal to kt. And the boundaries for this would be from a naught to at. So I can write this as AT raised to power of 1 minus n minus A naught raised to power of 1 minus n by n minus 1 is equal to KT. Correct? Now, this is for nth order. Correct? So this is the equation which you will get for the nth order. Now the T50 for nth order, T50 for nth order implies AT should be equal to A naught by 2, which implies A naught by 2 raised to power of 1 minus n minus A naught raised to power of 1 minus n by n minus 1 is equal to K into T50. So therefore, K into T50 is equal to 1 by 2 raised to power of 1 minus n multiplied by n minus 1, that into A naught raised to power of 1 minus n here. Correct? Sorry. A naught I need to take on my mistake. A naught. Let me rewrite that. A naught raised to power of 1 minus n divided by n minus 1, that multiplied by 1 minus 2 raised to power of 1 minus n by 2 raised to power of 1 minus n. Correct? So this is what you will have. Okay. Or you can do one thing. Instead of writing this 2, if I take it to the numerator, that will become 2 raised to power of n minus 1. So 2 raised to power of n minus 1 is what I can write. So 2 raised to power of n minus 1 minus 1. Now notice this carefully. T50, if I write in terms of these terms, you will see it is dependent only on A naught. Rest of them are constant as long as we know the terms here. So therefore I can say T50 is directly proportional to A naught raised to power of 1 minus n. So for two different initial concentrations, for two different initial concentrations, we can have T51 by T52 is equal to A naught 1 by A naught 2 raised to power of 1 minus n. The rest of the things will anyway get cancelled. Sorry. Now, we can use this logic to calculate the nth order kinetics. So that is implies A naught 2 by A naught 1 raised to power of n minus 1 is equal to T51 by T52. If I take ln on both sides, I'll get n minus 1 into ln A naught 2 by A naught 1 is equal to ln T51 by T52. Got it? Therefore, if I write this as n minus 1, that will be equal to ln T51. 1 second, just give me a second. Sorry. So ln T51 minus ln T52 by ln A02 minus ln A01. So that implies the order calculation can be done like this: 1 plus this entire thing ln T51 minus ln T52 by ln A02 minus ln A01. So that will be the nth order kinetics. Clear, everybody? So please quickly check this out. So this is one of the methods by which you can calculate the order of the reaction. What are the other methods? See, one method is a units of rate constant. Generally, when we write rate, rate is equal to constant into a raised to power of x into b raised to power of y. Rate constant will be equal to rate units, which is molarity per second, divided by molarity raised to power of some nth order. So if I take this m in the numerator, it will become m raised to power of 1 minus n. So if n is equal to 0, the units of k will be molarity per second. Okay, molarity is mole per liter per second. So if you see these units for rate constant, which means you are talking about zero order kinetics. If you see n is equal to 1 and you get second inverse, that means it is about first order kinetics. If you see molarity inverse and second inverse, it is second order kinetics, and so on. These are all the ways to figure out the order of the reaction using the units. Got it? Next. In case if you want to figure out the rate constant for complex reactions. For complex reactions, we have adaptation of two methods. One is equilibrium method, the other one is steady state method, right? How do we figure out the rate order of the reaction using these two? Let's see. And in fact, this is also used to identify the exact rate expression also. See, let us talk about one complex reaction like formation of O2 from O3. The overall reaction includes 2O3 giving 3O2. This is the overall reaction. Step 1, if you notice, O3 is giving O2 plus O. This is the first order kinetics. Okay, I mean in forward direction as well as backward direction. So O3 is giving with a rate constant K1 in the forward direction and K2 in the backward direction. And usually equilibrium reactions would be fast. Then the O3 which is there is also again reacting with the nascent oxygen released to get this as O2, but this is happening slow. Hence, we can say in the first step and second step, this O is common one, and that is not a part of the reactant and it is not a part of product. So anything which is not a part of reactant and product and just happening within the reaction, those are intermediates. So rate expression should be always represented in terms of reactants and products and not in terms of intermediates. Now, if you write the rate law expression, you see it should be written only for slow step. The slow step is always the rate determining step. So therefore, rate can be written as K3 multiplied by O3 multiplied by O. So O3 has only one stoichiometric quotient, one here. And you know that every step in a complex reaction is an elementary step. So therefore, K3 into O3 power 1 and O power 1. Now I need to somehow eliminate this intermediate. For that, we can use the equilibrium method, right? So how do we do that? So first, equilibrium method. First, I'm writing equilibrium method. As per equilibrium method, first you write the equilibrium constant for the given equilibrium reaction, which is equal to O2 concentration into O concentration upon O3 concentration, upon O3 concentration. And K equilibrium is equal to K forward by K backward, which implies nascent oxygen is equal to K1 by K2 multiplied by O3 multiplied by divided by O2. This will be the nascent oxygen form. So I can write rate is equal to K3 into O3 power 1 into O2. So O2 into O, which is K1 by K2 multiplied by O3 power 1 divided by O2. So which implies K3 K1 by K2, sorry, which implies rate is equal to K3 K1 by K2 into O3 raised to power of 2 divided by O2. Now you can see in the rate expression, you only have reactants and products. Therefore, order of the reaction, order of the reaction is equal to 1 because this is 2, 2 minus 1 will make it 1. So that is the order of the reaction. This is using equilibrium method. Got it? I hope all of you understood how the equilibrium method needs to be adapted. The next one is steady state method. Okay. The next term is steady state method. Steady state approximation is the other term used. SSA, steady state approximation method. Here, what we assume is whatever the intermediates which are forming, their rate is always constant. Okay. Sorry, the concentration is always constant. So if the concentration of the intermediate is constant, that means the rate of change is zero. So that's what we are trying to say. The rate of change of intermediate is always equal to zero because it will always have a constant concentration. Of course, when we use the word steady state, we are expecting that the intermediates are steady, which means they are remain at a constant concentration. Hence, now we know that this was the overall reaction. This is step 1, this is step 2. Using this, we can say, right, K3 is the rate determining step. So now, again, if I write the rate expression, rate R should be written for slow step, which is K3 into O3 into O. But again, our idea is to eliminate these intermediates. So one thing we know that as per SSA, this should be equal to 0 as per SSA, which implies rate of change of intermediate will be equal to where is the intermediate forming in this step 1 and step 2? You can see it is forming in the forward direction, losing in the backward direction, again losing in the forward direction. So I can write this as K1 into O3 concentration minus K2 into O2 multiplied by O minus K3 into O3 multiplied by O. So check, it's gaining in this direction, losing in this direction and losing in this direction. This is the net rate of intermediate and that must be equal to 0. Okay, that give to Tata. So if this is equal to 0, so we can say K1 into O3 is equal to K2 into O2 minus K3 into O3, this whole multiplied by nascent oxygen. So from here, the nascent oxygen is equal to hmm, K1 into O3 divided by K2 into O2 minus K3 into O3. This is the intermediate concentration at steady state. Let me put this back into this equation. So from here I can write rate law expression R is equal to K3 into O3 multiplied by K1 into O3 divided by K2 into O2 minus K3 into O3. This is the actual rate law expression. Got it? Now, here we need to approximate a bit. Now, notice something. Usually, when you have equilibrium reactions, right? This direction reaction and this direction reaction, they will happen to go faster. Forward reaction, backward reaction goes faster. To attain the equilibrium faster, because it is a fast step, so we definitely expect that the forward and backward reaction is happening faster. And this reaction is slower, which expect that this value should be lower. So K1, K2 values are generally very high compared to K3. Okay, so we know that since K1 and K2 values are far greater than K3. So we can say that this K3 can be ignored. This K3 can be ignored here. Hence, we can say rate will be now equal to K3 into O3 concentration into K1 into O3 concentration upon K2 into O2 concentration, which is equal to K3 K1 by K2 into O3 raised to power of 2 by O2 concentration, right? So have you noticed that this is the exact same expression we got even from equilibrium method? This is the same expression we got from equilibrium method also. So therefore, order of the reaction, order of the reaction in this case is 1. Clear? So everybody, please go through the steady state approximation method quickly. Check. Let's try it together. Let's try this question together. Check out. A is giving B plus C. It's a fast reaction. And A plus C is giving B plus D. It's a slow reaction. So K2 is the rate determining step, correct? As per the question. This should be the rate determining step. And overall, 2A is equal to 2B plus B. Now the question was asked like this. This was a JE question only. B is an intermediate using steady state approximation. The order is 1. C is an intermediate. Rate constant is K1 by K2. So let's use the SSA. Using SSA, what we can say, the rate of change of the intermediate should be 0. And you can clearly notice that the concentration C is the intermediate. So hence I can say K1 into A, which is the formation in the forward direction, minus K2 into A into C, which is the formation, which is the loss of rate in the forward direction in second equation, correct? So that should be the net rate change of C. So from here, you can see that A will get cancelled. So concentration C will be simply K1 by K2. Now if I write the rate law expression, rate will be equal to, rate will be written for slow step, which is K2 into A into C. So that is equal to K2 into concentration of A into concentration of C is K1 by K2. So K2, K2 will get cancelled. So rate will be equal to K1 into concentration of A. K1 into concentration of A. So therefore, order of the reaction, order of the reaction is equal to 1. Clear? So check out, is B is intermediate? No, this is incorrect. Using this order, we got it as 1. This is correct. C is an intermediate, which is also correct. Overall rate of the reaction is only K1 and not K1 by K2. So this one is also wrong. So you can see B and C are the correct option, correct answers in this case. So I suppose all of you understood this part, right? That was a simple one. Okay, I want all of you to try this one also. Check out another simple question. Find the order of the reaction for 2NO plus Cl2 is giving 2NOCl. Doubling concentration of both reactant increases the rate factor by 8. Doubling concentration of Cl2 alone will give you rate as double. Please do it. and I'm sure most of you got this. So first, if I write rate in terms of this one, I have to double it on both sides. Once only chlorine need to be doubled. So I will get this as R1 by R2 is equal to, right? You can see 1 by 2 raised to power of x into 1 by 2 raised to power of y. So implies 2 raised to power of x plus y is equal to R2 by R1. And that is given as 8 times. So which means 8, which is 2 raised to power of 3, implies x plus y equal to 3. So directly we know that from here only. Second step is not honestly required, but if you want to know the rate with respect to individual reactants, so what we can do, we can use R1, R3 by R1. So in that case, R3 by R1 makes the x term gets completely cancelled. So we'll have only 2 raised to power of y, which is given as the rate will double. So 2 raised to power of 1. So that implies y is equal to 1 and x is equal to 2. So those are the orders with respect to the reactants. Clear? Now, what if you have an experimental data and I need to find out the order? Use the same logic here. Try to figure out what is the order of the reaction for this case. Quickly, try that, everybody. Let's see. The next part of this topic is about understanding something called Arrhenius equation, which suggests how the rate constant is dependent on temperature. Okay. See, the rate constant of any reaction K will be given as an empirical formula, which is A e raised to power of minus EA by RT. This is empirically derived. Empirically derived as in with different experimental data, we will be able to use that data and convert that into a formula, which is this one, where A is termed as pre-exponential constant, and as per Arrhenius theory, it is suggested that it is independent of temperature change. EA represent activation energy, which we introduced this to ourselves initially, that this is the minimum amount of energy that is required for a reactant to form product. Yeah. Okay, so that is E naught is greater than E naught is greater than 0. You notice that from a reactant R, if you are going towards product P, then this value represents activation energy in the forward direction. Ajay, if I ask you what is a backward direction, then this value represent the activation energy in the backward direction, by chance if it is asked. Okay. Now, delta H of the reaction implies the product enthalpies minus reactant enthalpies. Correct? And if delta H is negative, that means it is exothermic. The graph which I have, I have shown it here. This is basically an exothermic change. If the reactant is here and it is going like this and stopping it here, then that is endothermic change. Okay. So K is equal to A e raised to power of minus EA by RT is the equation, in which if I take this entire term, that is an numerical term, e raised to power of minus EA by RT, that is basically fraction of particles which got enough energy to cross the barrier of activation energy and then try to form the products. Got it? So these are the fraction of particles. For instance, if we talk about air particles, like nitrogen and hydrogen are colliding with each other continuously, but even after the collision, they are not forming into some products like NO gas or NO2 gas. Okay, so you will get this as either NO or NO2 gas. We don't get that, right? So even after reacting N2 and O2, or we are colliding with air particles with each other. Now, why they are not able to form into products? Reason is very simple, that despite making collisions, they are not able to cross the energy barrier. The collisions are happening, but they are not getting that enough activation energy to cross that highest energy form to convert into products. But this could still happen, usually uh, the air particles when they are in clouds, okay, and when the lightning happens or there is extremely high amount of temperature and pressure provided, then N2 and O2 can cross that energy barrier and convert into NO gas. Okay, an electrical arc can help it, break those N2 and O2 bonds and convert into NO. So the activation energy for air particles to convert into products is very high. Okay, now if you have to write it mathematically, you can see K is A e raised to power of minus EA by RT. If I take log on both sides, I'll get ln K is equal to ln A minus EA by RT. In terms of log, you'll get this as 2.303 log K and this entire thing. Now you can write this as a equation of a straight line, which is y is equal to, mx plus c. C is a constant here, which is y-intercept log A value, and tan theta is equal to minus EA by 2.303 R. Okay. What are the factors that affect the rate of the reaction? That is rate constant of the reaction. The first factor includes catalyst. Now, catalyst is anything which will increase the rate of the reaction by finding an alternative path. So, in case if there is any alternative path, right? So that is where the catalyst will be used. I mean, that is where the catalyst is going to identify that which has lower activation energy and go through it. Got it? For example, if this is a reaction from reactants to products originally without catalyst, so it has a high activation energy. But with catalyst, it may have found a low activation energy path. So now this EA dash, which is with catalyst, is lesser than EA. Got it? Second, adding catalyst will decrease the activation energy. It does not change the reactant or product energies or overall enthalpy of the reaction. In fact, catalyst does not impart any change. This I told you already just now, that it does not change internal energy, free energy, enthalpy, or K equilibrium factors. If K1 is without catalyst, I can write it as A e raised to power of minus EA1 by RT, and with catalyst I can write it as minus EA2 by RT. I know that EA1 value is greater than EA2 value. Okay. So if we divide these two, we will get e raised to power of minus EA1 minus EA2 by RT, or minus delta EA by RT. So ln K1 by K2, if I write that, I can get minus delta EA by RT. So from here we can get that delta EA, which is the difference in the activation energy which was created due to adding catalyst, will be equal to RT ln K2 by K1. Correct? So this is the difference that is created by difference in activation energies. Clear? Next. Second thing, as the temperature, first one we use this catalyst, correct? Due to catalyst, the activation energy changed, and how it impacted, we just saw that. Second thing, what if there is a temperature change? See, if we had K1, which is at temperature T1, this is the equation of the rate constant. If we have K2 at temperature T2, this is the equation of the rate constant. Yeah. Okay. One second. So check out. If you divide these two and take log on both sides, so I'll get ln K1 by K2 is equal to minus EA by R into 1 by T1 minus 1 by T2. So one thing you need to understand that EA is an intensive property. That means it only depends on the nature of that reaction. So just because increasing temperature or decreasing temperature, EA does not change. So as for this, what we assume, EA and A are independent of temperature, independent of temperature for a particular reaction. Got it? Hmm. So we will get ln K1 by K2, that is equal to minus EA by R into this term. Now this goes almost very similar to that of an equilibrium constant formula which we derived for two different temperatures in terms of delta H of the reaction, which we call it as Van 't Hoff's equation. Correct? So ln K2 by K1 is equal to delta H of reaction by 2.303 R into 1 by T1 minus 1 by T2. Okay. Now, if you may recall from states of matter, we learned something, that is the fraction of particles uh, which have similar speeds. If you plot them, then we found this to go like this, isn't it? And this was its temperature T1. And as the temperature increased, you can see this is the way the graph keeps going. So this will start becoming more and more flatter as the temperatures start increasing. Now imagine the same thing, just that the fraction of particles here, instead of with respect to velocity or speed, you change that with respect to kinetic energy of particles. So I can say if the kinetic energy of particles versus the fraction of particles, correct? So if we compare these two, kinetic energy versus the fraction of particles here, if you plot the fraction of particles at a temperature T1, then this is how the kinetic energy changes. And this will be the kinetic energy change. And the same thing you will notice that as the temperature increases, the peak values decreases. And you know that there is one particular value which is one particular kinetic energy which is same as the activation energy, and after this everything which is crossing this point, that means they will convert into products. So you can see this much is the fraction of particles which are converting into products. Okay, because if you may remember that area under the graph will give you the total number of particles I mean will be equal to 1, which is sum of all the fraction of particles, correct? Similarly, if I take this one, this is the fraction of particles which are crossing the barrier, correct? And here this will be the fraction of particles which are crossing the barrier of activation energy at temperature T2. So it is clearly visible that as the temperature increases, one second, you can see as the temperature increases, you can see more number of particles are actually crossing the barrier. So from here, one thing we can say, rate always increases in one direction when you're talking, either in the forward direction or in the backward direction. Rate always increases as the temperature increases. Why? Because the rate constant is directly dependent on the temperature term. So if temperature increases, rate constant increases, hence rate of the reaction increases. So you can see as the temperature increases, number of particles crossing the barrier to form products increases. Now I can say, if suppose experimentally at temperature T1 is equal to 300, I'm finding the rate constant as K1. And at temperature T2, that is after increasing 10 degrees, again I'm finding the rate constant, this time I'm getting it as K2. Approximately what has been found for most cases, the K2 value is almost double the K1 value. That means for every 10 degrees temperature change, the rate constant increases by 2 times approximately. In fact, to be precise, that range will be somewhere between 2 to 3. In some cases, it will be 3, but in majority of the cases, it will be close to 2. Okay. This is what we define as temperature coefficient. So temperature coefficient is the rate constant at T plus 10 versus rate constant at temperature T. Suppose if you have 300 kelvins, at that the rate constant is K. And suppose if I say mu is equal to 2, then to go to temperature 360 degrees, how much rate will increase? You can see 2 times, 2 times, 2 times, 2 times, 2 times, and 2 times. So from 300 to 360, these many times the rate increases. So that means it goes 2 raised to power of 6 times. If I have to generalize this, that is rate constant at temperature T plus delta T is equal to 2 raised to power of, this will be total change difference divided by 10. So delta T by 10 into KT. Now this was assuming that is changing 2 times. What if changes some mu times? Mu is what we call it as the temperature coefficient. So mu raised to power of delta T by 10 is equal to KT plus delta T by KT. Very important formula for us. Got it? So whenever you want to check out how much amount is the rate change or rate constant change, you can always use temperature change whenever we are talking about the temperature coefficient change. Clear? I hope all of you understood this, how the temperature coefficient influence is observed. Okay. So this is how much it has been given in NCRT. Everybody clear? So for today, we'll stop it here.